We only have one objective for today, which is by the end of class, you should be able to use all the stoichiometric functions to convert between moles of unknown substance to an unknown substance, or between moles to grams or grams to grams, using the molar ratios given to you in the equation and the molar masses that we'll derive from the periodic table. Sound good? All right, we went over this a little bit yesterday, but reaction stoichiometry, which is what this whole chapter is based on, is just the relationship between the masses of the reactants and the products in a chemical equation. So when you're studying stoichiometry, you're studying that relationship between their masses. It requires a balanced and accurate chemical equation. So if you thought we were done balancing equations, I am sorry to tell you we are not done balancing equations, and we are also unfortunately not done naming compounds or going from a name to a formula. That's going to be a skill that you're going to continue to need as we go through things. Okay. Sometimes you will be provided with a balanced chemical equation. Sometimes they'll provide you an unbalanced one and you'll have to balance it. And sometimes you will not even be provided an equation. They will give you a word equation and you're going to have to change it into an equation and then balance that equation. So there will be varying levels of difficulty when it comes to equations. You will also need molar masses for both the reactants and the products, which are rarely given to you. You will most often have to get them from the periodic table, but it looks like from our bell ringer that most people still remember how to do that. So that's awesome. We don't have to go through that step by step again. And then you're also going to need a molar ratio. Molar ratios can be derived from the balanced chemical equation. All right, we arrive at our first practice problem of the day. I would like you to write all the possible mole ratios for the following equation, and then also all of the molar masses for the following equation. So you're going to need to write me a mole ratio between aluminum oxide and aluminum, and between aluminum oxide and oxygen, and then between aluminum and oxygen. Okay, so there should be a bunch of sets of mole ratios, and then give me the molar mass for each compound or element. Diatomic element. Okay. All right. So, to start with the ratios, if we're doing a ratio between aluminum oxide and aluminum, then the ratio should be 2 to 4, which we could simplify down to 1 to 2. Okay? So, if you were going to write a conversion factor for this, for aluminum oxide to aluminum, you could write it either as 2 aluminum oxide over 4 aluminum, or you could write it the other way around. Oh, and it should say moles in here. You could flip it the other way around and write 4 moles of aluminum for every 2 moles of aluminum oxide. And again, you could simplify this down to 2 to 1 or 1 to 2 if you want to make the math easier on the problem, because it does reduce. We have 2 conversion factors because sometimes we'll be going from moles of aluminum to moles of aluminum oxide, and sometimes we'll be going from moles of aluminum oxide to aluminum, and we want to make sure that we're able to cancel out this portion of the units so that we wind up with the units we want. So it's important to pick the appropriate conversion factor. Then if we wanted to do to oxygen, then the ratio would be 2 to 3, and that does not reduce. So then you could again write out 2 moles of aluminum oxide to 3 moles of oxygen. And you could flip it and do it the other way as well. And then the last one that we should be looking at is between aluminum and oxygen. So that ratio would be 4 to 3, doesn't reduce again, and again, you can write, 3 moles of oxygen to 4 moles of aluminum, and you can flip them and write them the other way as well. These conversion factors are important for later on. When it comes down to it, really all you are doing is looking at the coefficients, so the numbers that are in front of the compounds, not the subscripts, which are these little ones down here. Those are not involved in mole ratios or in conversion factors. We're just looking at the coefficients in front of them and using them to help us make a ratio. Then, as far as molar masses, what did we come up with for aluminum oxide? Al2O3. We've got 101.9, you said 57? Okay, and that would be because aluminum has a mass of 26.98, and there are 2 of them, and then oxygen has a mass of 16.00, and there are 3 of them, so that comes out to be pretty large molar mass. And then because our book rounds to 4 decimal places for the molar masses that it provides, we'll round our final molar mass to 4 decimal places, and that would be 1, 2, 3, 4, or not 4 decimal places, 4 significant figures. And we'll look here, so we would actually round it up to 102.0, and then unit grams per mole.
How did we get that number again?
How did we get to this number?
Yeah.
We took aluminum, and we look at the periodic table, and we say that it has a molar mass of 26.98. And then we have to take that times 2, because in the problem there are 2 aluminum atoms. And then that comes out to whatever number it comes out to when you multiply it. And then oxygen has a molar mass of 16.00, and we have to take that times 3 because there are 3 oxygen atoms in this. And then when you take whatever those numbers are and you add them up, that's your final molar mass. That's how we get to that number. Little review. It's been a while since we've done molar mass. And then what molar mass did we come up with for the aluminum?
26.98.
Yeah, because it's just a solitary aluminum atom. The 4 in front of it tells us that in this equation, it would produce, if we were just breaking down, the starting material, 2 molecules of aluminum oxide, we would wind up with 4 aluminum atoms. That's what that number tells us. But when we're looking for the molar mass of aluminum, all we have to do is look at the periodic table. For oxygen, it's a little different because this isn't just a solitary oxygen, it's an oxygen bonded to an oxygen, and we know that because of the little 2 underneath. So for oxygen, the molar mass would be 16 plus 16. So, what is that? 32? My brain's not doing quick math today, but 32 would be your molar mass for oxygen then.
And do both of those have grams?
Yes, they should all have the molar mass unit, grams per mole. Further into the belly of the beast that is stoichiometry. Okay, it's important to remember as we start to get into actually doing stoichiometric calculations that this is all idealized theoretical math. So we're saying that when we do this math, that under ideal circumstances where all of the product or all of the reactants became exactly the product that we want, this is how much we would end up with. But in real life, when you run this in a lab, you will discover that it is not 100% accurate in experimentation, and that's because sometimes the reactants that you start with are not pure reactants, right? So you might have aluminum oxide, but it might be a little bit impure, so there might be other elements in there that you don't know about. And as a result of that, you might wind up with some of the product you expected, but then also some byproducts you weren't expecting. And so you might not have 100% of the yield you thought you were going to have. So as we get into doing actual stoichiometry, and you'll get to do some equation or some reactions in the lab, and you'll do the stoichiometry math to find out what your yield should be, and then you'll do the actual reaction and weigh it to find out what your yield actually was. There will be some calculations to find out percent yield and whether or not your things were as accurate as they could be. So just a thing to keep in mind. What we're doing now is the pure math of it, which both chemists and physicists like to idealize things on paper. So this is, if everything was perfect, this is what should happen. Real life is often messy and imperfect. We're going to discuss and practice 4 types of stoichiometric problems. We previewed what those problems look like yesterday, so we'll review that, and then you'll get to do an example problem for each type of problem where you practice this new skill. All right, type number 1, conversions going from moles to moles. So in this type of problem, you're going to convert an amount of a given substance in moles. So they'll tell you, you have this many moles of this substance. And then you're going to be determining an amount of moles of an unknown substance. So they'll say, how many moles would you come out with at the end of the problem? This plan requires only one conversion factor, and that conversion factor is the stoichiometric mole ratio of the unknown substance and the given substance from the balanced equation, which is a long way of saying you'll need the mole ratio and a conversion factor of some kind that we learned how to produce in the previous practice problem. So the picture of what this will look like is you're going to start with a given amount of a substance over here, okay? So they're going to say you have X moles of this substance. So then you're going to take the moles of your substance you're converting to and put them on the top, the moles of the substance you've been given on the bottom. This is your mole ratio that you'll get from the balanced equation, and that should end up with the moles of the given canceling and leaving you with moles of unknown substance. This is the simplest form of stoichiometric problem. You don't need any molar masses. You only need a balanced equation in order to do it. So, to practice this, I'm going to give you an equation, and I want to know how many moles of lithium hydroxide would be needed in order to react with 20 moles of carbon dioxide. So in this equation, you'll see that both carbon dioxide and lithium hydroxide, which is this substance right here, are both on the reactant side. But you can still write a mole ratio between them to do a conversion. So even though they're on the same side of the reaction, you can still figure this out using the balanced equation. So start by drawing yourself out a little picture of where you're starting and where you want to end. Get your conversion factor in the middle and try to convert. So to set up, we have to start with our starting substance. So we know to begin with we have 20 moles of CO2. Okay? And by the time we get to the end of this, we're hoping to have some number of moles of lithium hydroxide, which I did not leave myself enough room to write. So somewhere in between, we need a conversion factor. So we're going to go ahead and look up at our equation and see we have 2, and then we have no number, which means 1. So the relationship between these is 1 to 2. Okay. We want to have lithium hydroxide be on the top of our conversion factor because that's what we're going to, and we want carbon dioxide to be on the bottom. So we would say that 2 moles of lithium hydroxide are present for every 1 mole of carbon dioxide. And then all that's left to do is run the math. So then if we do the math, we can erase our question mark because 20 times 2 comes out to 40. So we should have 40 moles of lithium hydroxide available to begin with if we would like to react it with 20 moles of carbon dioxide. Okay, let's switch back and talk about the second type of problem. This is going to be moles to grams. This is converting an amount of a given substance at the start that's in moles to an amount of the unknown substance that will be in grams. This plan is going to actually require 2 conversion factors because you will need to convert first using the mole ratio to get moles of unknown substance, and then you will need to convert moles of unknown substance into a mass in grams, which will require the molar mass of the unknown substance. So what this looks like here is you're going to have your starting amount of a substance in moles. You'll use your mole ratio to make a conversion factor here. Then you will use your molar mass conversion factor to get to your final product. So the first half of this problem will be identical to what we just did, and then there's just one more step on top of that at the end. So we can move to the example problem. In photosynthesis, plants use energy from the sun to produce glucose, which is C6H12O6, and oxygen, which we know is diatomic, from the reaction of carbon dioxide and water. So what they're saying here is you have reactants, carbon dioxide and water, products, glucose and oxygen. What mass in grams of glucose is produced when 3 moles of water reacts with carbon dioxide? So what do we immediately notice is different about this problem? Anybody? We don't have a balanced equation. So that should be step 1. All right, so they gave us the names of our reactants. We have carbon dioxide, and we know we have water. And then there is energy involved, but because energy isn't going to provide any atoms, we're not going to list it in this equation. But the products of this reaction should be glucose, C6H12O6, and oxygen, which we know is diatomic. So to balance this, we got to start by figuring out how many atoms of each we have on each side. So on this side of the equation, on the starting side of the equation, how many carbons are involved? One carbon atom. How many oxygen atoms? 3 total. And how many hydrogen atoms? 2. On the second half of the equation, how many carbon atoms? How many oxygen atoms? 8. And hydrogen atoms? 12 hydrogen atoms. Okay, so to begin with, the general rule is if you have anything other than oxygen and hydrogen, start with those. So let's try to balance the carbons. What should we do? Yeah, we'll put a 6 in front of the CO2, and that would leave us with 6 carbons. But it's also going to change our number of oxygens, isn't it? What's it going to change it to? 12 plus 1, so we'll be at 13. Okay. Now, let's see. The next thing I would suggest is, because we have an even number of oxygens on the right-hand side of the equation, and they have even subscripts on them, it's going to be impossible for us to end up with an odd number of oxygens on the right-hand side of the equation, which means the number on the left-hand side needs to also be even. And the best way to do that is to put an even number in front of the water. Okay, so what number could we put in front of the water that would be even, but that might maybe try to balance our hydrogens?
6.
Yeah, let's try 6. So if we put 6 in front of this, that goes ahead and changes the hydrogens to 12, and then it's going to change our number of oxygens. We still have 12 oxygens from the first, but now we have 6 additional ones from this, so 12 plus 6 is 18. 18 oxygens. Okay. Now, we don't have 18 oxygens on the right-hand side, correct? How could we try to get to 18 oxygens?
By putting a 6 in front of the O2.
Okay. 6 in front of the O2. Then we are going to have 6 oxygens from the glucose, as well as 12 from the oxygen, which would bring us up to 18. And now we appear, at least, to be balanced, yes?
Mm-hmm.
So this equation right here is the one we are going to want to use then to get our molar ratio for the next half of the problem. So I'm going to erase the equation off of my screen in a moment, but before I do that, let's identify what 2 substances we are converting between so we can get that molar ratio. We're starting in the problem with moles of water, and they want to know reacts with carbon dioxide. So we're going to be looking between these 2, which means the ratio is 6 to 6, which we could reduce down to 1 to 1, right? So just knowing that to move forward with the problem, go ahead and try and set up the next half of your problem and convert. Okay? Yeah, let's look back at the question. I didn't read carefully enough. They want us to end up with a mass of glucose. So grams of glucose reacting with 3 moles of water. They put carbon dioxide in there as a distractor, and I fell for it.
They worded it really.
They did. They were trying to trick us. So we're actually not going between, this is the wrong molar ratio then, because we're not going between water and carbon dioxide. We're going between water and glucose. So then if we look at that, here's glucose. So the molar ratio is actually 6 to 1. So let's keep that in mind then. And we'll go ahead and have this problem be your bell ringer at the start of class tomorrow. So if you have the setup pretty much ready, then at the start of class tomorrow, we will go over the answer.